Thank you. Yeah, so I'm going to be talking about nearby galaxies and their central black holes, and our efforts to try to understand how they co-evolve. In particular, I'll be discussing a large program using Gemini NIFs assisted by adaptive optics. So supermassive black holes reside at the centers of essentially every massive galaxy. And of course, we now have very strong evidence for the presence of supermassive black holes. The best dynamical evidence we have comes from our own galaxy, where we can track the paths of individual stars as they orbit about the black hole. But beyond the Milky Way, black holes have been dynamically detected in about 100 galaxies to date. And from those detections, we've learned that the masses of black holes correlate with the large-scale bulge properties of the galaxy. So two of the more well-studied relations are between the black hole mass and the stellar velocity dispersion, that's m sigma, and the black hole mass and bulge luminosity, that's ml. So these relationships suggest that somehow black holes and galaxies grow in tandem. However, the local black hole mass census is highly incomplete. And that's particularly true for low mass black holes, below about a few times 10 to the 7 solar masses, and for high mass black holes above about a few times 10 to the 9 solar masses. So this leaves major questions regarding the distribution of black hole masses with host galaxy properties. With the present measurements, things like the slope, the intrinsic scatter, and even the shape of the correlations for low and high mass black holes are not well established. Also, as we begin to study a wider range of galaxies, we find surprises in the scaling relations. For example, recent progress detecting high mass black holes in brightest cluster galaxies hint that these objects could lie above m sigma, but there's still too few available measurements to firmly characterize the scaling relations at the high mass end. And the uncertainties are equally severe at the other end, where spiral galaxies with low mass black holes exhibit large scatter below both the m sigma and ml relationships. In addition, we still don't have a good understanding of the primary physical mechanisms that are driving these empirical correlations, and there's plenty of fundamental questions that remain unanswered. For example, do black holes and galaxies grow in lockstep with one another over time, or does the growth of one precede that of the other? So in order to answer those kind of questions, we really do need more black hole mass measurements, especially at the extremes of the black hole mass scale and over a wider range of galaxies that have undergone different evolutionary histories. So in order to obtain robust black hole mass measurements, we need high angular resolution observations that probe the innermost regions of galaxies where the gravitational potential from the black hole dominates. So that region is the black hole's sphere of influence, and its size is pretty small. So for a typical supermassive black hole with a mass of about 10 to the 8 solar masses, the black hole's sphere of influence is roughly tens of parsecs. So therefore, we're really limited to studying only the nearby galaxies with the current observational facilities. So in the past, HST, with its angular resolution, has played a fundamental role in detecting black holes over the past about 25 years. But more recently, progress has been made using adaptive optics, AO, on large ground-based telescopes. So AO can deliver similar angular resolutions as HST, but it has the advantage of being used with a larger telescope, and it operates in the near infrared. So galaxies that were previously pretty tough to observe with HST because they were a little too faint or a little too dusty can be studied in great detail with AO on large telescopes. So given the extensive observational efforts that are needed for just a single black hole mass determination, the approach that has been used for years is to measure one or a few black holes at a time. But what we also need to do, and in order to advance the field, is examine larger samples with homogeneous data sets. And so we're carrying out a large black hole program at Gemini North. So we're going to be measuring black hole masses using stellar dynamical modeling methods in 31 galaxies using AO-assisted NIFs. So the goal of this program is to obtain a more complete census of local black holes in a wider range of galaxies. So here I'm showing a plot of the galaxy K-band luminosity and size, the effective radius. The green dots show the published dynamical black hole mass measurements that have been made, And for comparison, the gray contours are showing the nearby galaxy population. So the point here is that those green points are not representative of the local galaxy population. So at a given luminosity, galaxies with smaller sizes have been preferentially targeted. They just happen to be the easiest to observe and model. But it's really important to sample this luminosity or equivalently mass size parameter space. So as you move away from these points in this direction, a whole bunch of different galaxy properties vary. Things like the stellar velocity dispersions, the mass to light ratios, the bulge fractions, the gas content, the stellar populations, and morphology. Also, galaxies that grow in different ways end up on different regions of this plot. So clearly, we need to do a better job of sampling this important parameter space if we want to get at what the true distribution of black hole masses are with host galaxy properties and try to really understand what role black holes play in galaxy evolution. So here in red are the galaxies in our sample. The red numbers correspond to the images that are shown around the plot. The red crosses are also in our sample. There's just no image being shown. So our sample significantly increases coverage of this important parameter space without sampling that already well-populated region within the dotted oval. So our sample spans a wide range of properties by design. For example, the stellar velocity dispersions range from 60 to 300 kilometers per second. We also have a number of spiral galaxies in our sample. We'll nearly double the number of black hole mass measurements that have been made in spiral galaxies, which is a regime that largely has not been tackled with stellar dynamical modeling techniques. So far, we have completed observations with NIFs for 12 galaxies, and those 12 galaxies already enhance the diversity of black hole hosts. So we've observed the largest, most luminous galaxy in the sample, as well as lower luminosity galaxies at different effective radii. And so here I'm just showing some example spectra from NIFs for the most recent 6 galaxies that we finished observing. So this is at the nucleus and then about an arc second away. And so the data quality really are excellent. So from those absorption features, we measure the velocity distribution of the stars along our line of sight. And we characterize that distribution by the center, the velocity, the spread, the velocity dispersion, and then asymmetric and symmetric deviations from a Gaussian, like H3 and H4, or even beyond. And so that's what I'm showing here for 2 example galaxies. So these are maps of the velocity, and we see that both of these galaxies are rotating. These are maps of the velocity dispersion, and we see this nice sharp rise in the velocity dispersion as you move in toward the nucleus, reaching values of about 375 and about 56 kilometers per second at the center. So again, you can see that we do have this wide range of galaxies. We also have some interesting cases. So in the case of this galaxy, the velocity dispersion drops at the center. So that could be an indication of a non-detection of a black hole, which would still be interesting because that would suggest that this galaxy lies well below both the current M sigma and ML relationships. But this could also be the result of a distinct dynamically cold component of stars at the nucleus as well. And so our dynamical models will be able to distinguish between those 2 scenarios. So in addition to the NIFS observations, we also have now completed HST observations for all 31 galaxies in 3 filters with WIFC-3. And we've also finished obtaining large-scale data as well. So we have IFU data with LRS-2 on the Hobby Eberly telescope, and then even wider field IFUs, Virus-P and Virus-W on the 2.7 meter telescope at McDonald. So what we're doing is constructing these orbit-based dynamical models. The main idea is that the galaxy's gravitational potential consists of contributions from the black hole, stars, and dark matter. The stellar potential is determined from, say, an HST image. We deproject it, assuming a viewing orientation and a mass to light ratio. And then we set up a representative orbital library, and we integrate orbits in that potential. We assign weights to the orbits such that the superposition best reproduces the observed kinematics from the spectroscopy and then the brightness from the image. And then we just calculate a whole bunch of different models varying the parameters of interest, like the black hole mass, and we're looking for the model that most closely matches the data. So here's an example for that first galaxy that I showed before, PGC 12557. And this plot kind of summarizes the modeling results. So these are contours of chi-squared as a function of black hole mass and H-band mass to light ratio. So ultimately, we're finding a black hole mass of 2.3 times 10 to the 9 solar masses. And then this is a comparison between the observed NIFS observations and larger scale LS2 observations in black and then best fit model in green. So the model is doing an excellent job of matching the data. So here we actually ran 4 independent orbit-based modeling codes that our team has access to. So they all operate, in that same general way that I described, but the details and the implementation are different. And so the good news is that we are getting consistent black hole masses, and it's also a decent way to try to get an estimate of possible systematic uncertainties too. Okay, so for this galaxy, it hosts a very massive black hole, and it's consistent with M sigma, but is a positive outlier from ML. And that's even when conservatively using the galaxy's total luminosity. So this galaxy is actually similar to a few other galaxies in the literature that I'm showing here in red. So all of these galaxies are nearby early type galaxies that are actually compact. So they do have small sizes, effective radii of 1 to 3 kiloparsecs, for their K-band luminosities of about 10 to the 11 solar luminosities. So that corresponds to stellar masses of about 10 to the 11 solar masses. And they have high central stellar velocities versions. So all of these galaxies host very massive black holes, but they're very different from the kinds of galaxies you would actually expect to find at the upper end of the black hole galaxy relations. So for example, here I'm showing some of the galaxies in the Perseus cluster. So NGC 1275 is the brightest galaxy of the cluster, and it's exactly the kind of galaxy that you would expect to find at the upper end of the black hole galaxy relations. So galaxies like this are large in size, typically effective radii of 10 kiloparsecs or more. They're often dispersion-supported galaxies, showing little to no rotation. So that's in sharp contrast to NGC 1277, which is located nearby, and it's an example of one of those compact galaxies. So as you can see, it looks very different from this galaxy. It is small and flattened and rapidly rotating. And instead, it looks quite similar to the typical redshift 2 massive quiescent galaxies, the so-called red nuggets. So these nearby compact galaxies look very similar to the redshift 2 red nuggets, and so they could be relics. So the redshift 2 red nuggets are thought to grow in size and mildly in mass through a series of mergers to produce the typical massive early type galaxy of today. So these local compact galaxies appear to have taken a different evolutionary pathway, one in which they didn't experience those same amount of mergers to build up the outskirts of their galaxies. If true, then these compact galaxies like NGC 1277 and PGC 12557 could reflect a previous time when the local ML relationship did not apply. Galaxies contained overmassive black holes, and it was the growth of the host galaxy that had yet to catch up. So it could suggest that black hole growth precedes that of the host galaxy. Another possibility, though, is that we simply don't have enough measurements at the upper end of the black hole scaling relations. So as I mentioned before, the form, the intrinsic scatter, all of that stuff is not well established at the high mass end. So these compact galaxies could lie in a tails of a distribution between black hole masses and host galaxy properties that have yet to be fully fleshed out. Okay, so that was an example of a stellar dynamical black hole mass measurement from the large program. And the large program was designed to do that kind of work. But in some cases, we're also seeing very prominent near-infrared emission lines. And so NGC 4111 is an example of that. So this I also mentioned earlier too. So this is a nearby galaxy that's an early type galaxy and it's edge on, and it has this dusty polar ring here. So this galaxy in the NIFS data has H2 emission lines, and this one molecular gas is embedded in that dusty polar ring. Now, there's also previously published stellar and ionized, so oxygen-3 gas kinematics from CERN through the ATLAS 3D survey. So the NIST data probe the innermost regions out to about 100 parsecs, and then the CERN data are larger scale that go out to about 1.5 kiloparsecs. So I already showed you these small scale NIST stellar kinematics. Again, the galaxy is rotating and there's a velocity dispersion drop at the center. The larger scale CERN stellar kinematics shows similar features too. If we look at the H2 kinematics from NIFS, so this is the velocity field, we see that it's counter-rotating with respect to the stars. So this is a map of the flux distribution for H2. So this side of the distribution is the brightest to the northwest, and we're taking that to be the near side of the gas distribution. So this near side is red shifted, whereas the far side is blue shifted, suggesting inflow. And then if we look at the larger scale oxygen-3 kinematics, the velocity field just looks different. So there's a kinematic twist here. And even if you were to try to pull out a global position angle, it doesn't align with any of the principal axes for NGC 4111. It's not aligned with the photometric major axis or the major axis from the stars. So basically, it's in this unstable configuration. So we examined the CERN kinematics a little bit further, applying kinematrry. So this is, again, that observed velocity map for oxygen-3. And so we're finding that this is actually a result of the superposition of two components. One that is rotating in the equatorial plane of the galaxy, and then one that's rotating in the dusty polar ring. And if we add this up and compare it to our observations, these are the residuals. And so this is supposed to represent the non-circular motions that are present in the dusty polar ring. And we see this kind of hints of a spiral-like structure, also suggesting potential inflow and connecting to the smaller scale H2 kinematics from NIFS. So with this analysis, we propose that this dusty polar ring originates from the capture of a dwarf galaxy. And again, that CERN ionized gas kinematics is the superposition of two components, one that's rotating in the main plane of the galaxy and one that is in the dusty polar ring. We do see the residual non-circular motions in the polar ring has this spiral-like structure, suggesting potential inflow that also potentially connects to the NIFS inflowing gas. So the H2 gas kinematics from NIFS, again, suggests inflow because the near side of the gas distribution is red shifted and then the far side is blue shifted. But some of this inflowing gas may be settling into the galaxy plane and forming new stars, which would result in that velocity dispersion drop at the center. But some of that gas does seem to be reaching the nucleus, triggering a low luminosity AGN. So yeah, this is just an example of how, the large program is focused on those stellar dynamical black hole mass measurements. But with the high quality NIFS data, we can also examine any emission lines and try to learn about black hole feeding and feedback. So very briefly, I want to end with kind of looking forward and giving an example of the potential impact with the James Webb Space Telescope. So we have a JWST program to study the very famous black hole in M87. So M87 has been the subject of a number of black hole mass measurements using both stellar and gas dynamical modeling techniques. So over the years, of course, the modeling methods and the data have improved dramatically, but the most recent stellar and gas dynamical black hole mass measurements continue to disagree by a factor of 2. Of course, we also have this image from the Event Horizon Telescope, and that provides a third independent measurement of the black hole mass. So at face value, this agreement between the EHT result and the most recent stellar dynamical black hole mass measurements, is reassuring. It's a good validation of the stellar dynamical modeling technique. But it does deserve further scrutiny only because both of these methods relied on extensive numerical modeling and built-in simplifying assumptions. So the original, not the original, but the most recent stellar dynamical black hole mass measurement was done by fitting axisymmetric orbit-based models to Gemini NIFS data assisted by adaptive optics. But there is room for improvement. So for example, the AGN dominates the inner region within about 0.3 arc seconds. And so the stellar absorption lines are completely diluted as a result. And so you can't actually make reliable stellar kinematic measurements very close to the center. So over here are the observations of the stellar velocity dispersion. And then that solid line is that best fit model from the most recent stellar dynamical black hole mass measurement. And so again, no measurements could be made within about 0.3 arc seconds, and then the model is unconstrained in that region. So with JWST and its very stable diffraction limited PSF and enhanced sensitivity and the need to not worry about residuals from skylines and telluric features, we can do a better job of measuring the stellar kinematics. We are also going to combine this data with new but already in hand large-scale IFU stellar kinematics, and we're going to apply a new triaxial orbit-based modeling approach. We're going to do a more comprehensive analysis of the error budget and include possible systematic effects like a potential mass to light ratio gradient. So yeah, JWST just provides this, exciting, timely opportunity to obtain a precise and accurate black hole mass measurement for M87, which is a key anchor to the black hole scaling relations. And since it looks like I am out of time here, I will just leave up my summary slide. Thanks.
Thank you. Okay, we have time for a couple of questions. Any question? The audience from Slack? No? So during you think about the question, I can give you a question. So 20 years ago, we thought that the sigma relation is very tight with the intrinsic scatter less than maybe 0.3 dex. Now the sample size is substantially grossly increased, including your measurement, and now scatter seems to be very large. So I was wondering what you think, whether this is, if the scatter is very large, then the correlation may not guarantee causality. So I'm wondering what you think about this.
Yeah, so I think at this point, we can measure the intrinsic scatter based on what we have and the uncertainties that everyone is quoting on their black hole mass measurements. But I really think everyone's doing the best they can. But I think there are a lot of systematics that are not being considered. I think we're getting down to the point where we actually have really excellent data in a lot of cases, and the statistical uncertainties are actually quite small. So I think as a field, we need to do a better job of examining those potential systematic effects and quoting more realistic uncertainties on our black hole mass measurements. That obviously ties into, how you're going to measure your intrinsic scatter. And I think something else that's really important there is doing it both ways, like with M87, right? So, we're seeing a factor of 2 difference, even though it's been measured many, many times in both ways. So I think before you talk about which relation is more fundamental or which one is a causality, or I think those kind of questions, you can try, but I think it all boils down actually to the uncertainties that we're quoting.
Okay, thank you. I think we have a question.
Joel has a question on the Slack. Do you expect the new IFUs being commissioned on juniors will provide any improvement for this kind of work?
It's a great question. I'm sure lots of people here are wondering the same thing. Yeah, so no, I think in our case, we actually don't quite need the really high R, the spectral resolution. We're not trying to study like dwarf galaxies or anything like that. So I think there's room to use it, and I'd definitely be interested in exploring that. I am actually very happy with NIFS. So, it's worth taking a look at. But yeah, NIFS seems very well matched to what we want to do, given its pixel size and, the larger space, the larger coverage, the larger field of view, and you don't need that super high R for the high res mode of GMERS.
Okay, one more short question.
I was intrigued by the amount of difficulty in 4111.
The amount of, sorry, what was
difficulty or complexity you have in the velocity field. So if you would take the same care for your more regular galaxies where you maybe haven't even checked if they also have a complex structure, would that maybe contribute to the scatter in the relation?
Yeah, so you're right. There's plenty of complexity in the gas velocity fields for 4111. I would never try to measure a black hole mass using gas dynamics for that galaxy, given the reasons that you just said. It's very complex.
No, but I was referring to other galaxies, whether even if you don't have necessarily a hint that it might be like that, but if you look at the larger scale, indeed, that might be, the galaxy might be more complex than what you think, and you actually could decompose, and then all of a sudden mass measurements are different.
Yeah, I mean, yeah, that absolutely could happen. Often what people do for gas dynamics is actually focus on circumnuclear disks. So they really aren't studying gas on large spatial scales. They're really focused in at the center, because then maybe you do see circular rotation and it's easier to model instead of trying to do everything all the way out. That definitely things can get messy with gas. Yeah.
I think we have to move on. So let's thank the speaker one more time.